Alright, folks. So, I just posted a video, part 2 of my impedance discussion. There's a third part I want to do, um, but I'm kind of, oh my god, I'm fucking way too high to do that right now. So, talk about something else, right? Well, I'll keep it electronics, though. Now, gone over resistors and capacitors. Next is inductors, but inductors are honestly really boring unless you're dealing with like really high frequency shit. Right? They're fucking just boring. But you kind of have to know a little bit about them. You're guitar players, and well, at least most of the people who I've run across are. So the guitar players out there, you know, you gotta at least want to know what's an example of an inductor, and there's lots of them, right? So easy ones to show. The speaker, right? If you look right here with the connectors, there's two little wires going off of that. They go inside here where you can't see. There's a little, they go down inside here. There's a little coil attached to this little cone inside here. And that little coil, it's a coil. That's an inductor. Coils are inductors. What's another example? Well, I don't have a, here we go. Transformer, right? It's actually two inductors in here. One significantly bigger than the other. This one actually has a way to get a couple of them. So I think this is some kind of a transformer from some kind of a amplifier of some sort, maybe meant for low power tube operation, because it's got a little two taps right here for just a what do they call it? Fucking warming plate for the fucking tubes, whatever the fuck it's called. And they have a nice little center tap right here, so it's got a couple of different options, right? And you got just the main input going on here, this side. But in essence, what you have is a coil here and a coil here, and changes in this coil induce current in the other current and the other coils, right? It's pretty simple. This one, the induced current the current induces a magnetic field in these coils, and it responds with this magnet right here, pushes it back and forth, causing this whole cone to shake and push sound out. And just so happens that the electricity that we use for the signal moves the cone in such a way that we can pretty much get any sound we want. Fucking crazy. And those are inductors, right? That's the simplicity of an inductor. Wow. Is it? All right. There's more to an inductor, right? So, an inductor is very much like a capacitor, right? They have some similarities, right? I don't know, just say. So, you've heard the expression the capacitor will block DC and pass AC. Well, the inductor does the exact opposite. It'll block AC and pass DC. Well, it doesn't necessarily block the AC, but it creates a level of impedance. And it's not necessarily that it has to be AC, right? Or DC. It just changes in the circuitry. It changes. It resists. It resists changes to the current. So that means is that when the voltage is going up, as it's going up, it's got a rate of change. This is also known as a derivative in mathematics. So the rate of change for this is what determines the impedance. Now, this can be written as a huge calculus formula, but if I wrote that all out for you, well, it'd get really complicated really fast. Luckily, we can just look at it in terms of a sine wave. And I know a lot of people out there are going to be like, what? What do you mean? Well, there's the properties, right? We just look at the frequency of a signal, everything. We can see how it works, right? So let's just think about this in terms of sine waves, because that's what we deal with the most. And we say this thing, as the frequency gets higher, the impedance gets higher. Higher frequency, higher impedance. With the capacitor, it's the opposite. Higher frequency equals lower impedance. This guy, it's just a coil inside there, right? So he holds energy in the magnetic field. Changes in the magnetic field are the result of changes in current. So if you put a current that doesn't change, a DC current through this thing, well, the only thing that's going to oppose the flow is going to be its resistance. Very little resistance in this thing. See my LCR meter here. See what we have as far as ohms. 117 ohms. It's actually a fairly decent amount of resistance, honestly, for such a coil. It's a good sized coil, though. I ain't gonna lie. Got a bit of weight to it, too. But let's see what his inductance says. Oh, about 100 millihenries, 96.8 to be exact. And this little number on the thing here, I don't know if that's a 6 or G. It just says 100 millihenries. That's it, 100 mH. So now we know that my meter works good. Yeah. So this much resistance, 100 ohms. I suppose I could show the DC is the same by putting another 100 ohms on there, running a volt through it, right? You'd see a half a volt on one side, and then I could put an AC signal through there and another resistor there, so you can see how it changes with frequency. But do you really want to see that? And the reason why I'm asking is because we'll have to get up to some pretty high frequencies to see anything, and let's face it, until I start skipping a bunch of frequencies, it's going to be a lot of looking at it and going, wow, man, I'm not seeing anything, right? So I don't know if I want to bore you with that much. All right, so instead of doing that, what I want to do is say what we should expect to see, right? Notice no cuts in the video, right? So, like I said, in an inductor, the impedance, which I'm going to represent with the letter Z. Actually, no, we're actually not talking about impedance just yet. We're talking about reactance. So, reactance is usually denounced with an X. For capacitors, we say XC. For an inductor, we say XL. Now, the reactance As the frequency gets larger, the reactance gets larger. So that means that we're not dealing with something that's in the denominator. We're dealing with stuff above the line. So we can say the denominator is just 1. We don't have to put anything in the denominator. But the formula is remarkably similar to that of capacitors. So it's actually going to be 2 pi times the frequency times the inductance, which we typically write with an L. All right. So this one's really easy to work with. It's about 100 millihenries, and we measured it. It's 96 point something other. But we'll just round it to 100, right? So we say that XL is equal to 2 pi times the frequency times 100 milli. Now, millihenries is a notation that tells you that you're going to multiply by some number, right? Milli means divided by 1,000. So we're going to write this as being divided by 1,000, which we will write as being times 10 to the negative 3. I do this because it's easy for the calculator, right? So we look at this and we got an XL. So let's say we want our reactance to be about, I don't know, 100 ohms, right? So what frequency will we need to get 100 ohms? Well, really all we have to do is just set our XL to 100. So we go XL is 100. And then all we have to do is divide that by 2 pi times 100 times 10 to the negative third, which really it's just divided by 10 at this point. But we have 100 and 100, so we can cross that off there. And then we have 2 pi times 10 to the negative third on the denominator. So that's going to be 2 pi over 2. So 1,000 divided by 2 pi approximately. So let's plug that into our calculator. See what we get. Fuck, I don't have a calculator with me. That's okay. Well, I got one. It's not my regular calculator, which I had in the living room the other day. So I always have a spare. All right, so 1,000 divided by parentheses 2. Where's pi on this thing? Pi there, and 159.15. Well, 155. So if this is right, this thing should give us 159.155 hertz, should give us 100 ohms. So now this is also with 100 ohms of resistance. So I have to do my proper due diligence here. So and we're going to assume perfection in this. So 141.42 ohms. Where have I seen that 141 before? Almost as if, oh yeah. Think about that for a moment. These numbers, they show up a lot, not on accident, but because of the the relationships that we see. So I'm going to get a 100 ohm resistor. I have a bunch of them right here. And these are really high tolerance, real tight tolerance on these resistors here. In fact, I would say this one probably is going to measure out pretty close to exactly 100 ohms. 99.3. Now what I'm going to do is I'm going to rig up a circuit very similar to the one I rigged up last week, where we're going to run a signal through this inductor, and we're going to measure just above this resistor. So we'll see the full signal, and we'll see the signal after the inductor, and we'll be able to compare the two. So I've got a DC source here. We want to keep it under a quarter watt. I really want to keep it under an eighth of a watt if I can, but it's because this inductor is not very thick wire. So let's see, what voltage should I do? Alright, let's see. Let's see here. Okay, so if I do a small enough voltage here, I should be able to get away with it. I'm just gonna do it with 1 volt for my DC. You guys will be able to see it. And I suppose I could do it on the oscilloscope. Looking at it, you'll be able to see that, you got the voltages, they don't change, and it basically just has the 100 ohms of resistance that you have there. So if I'm right? If I'm right. Well, back to 1 volt. This is my ground. Put it on the other side of the resistor. And this is my source. Positive voltage, I should say. On this side of the inductor. And turn on my oscilloscope. My silly scope, I call it. Now, if you're interested in doing electronics, and I would hope that you are, because you're wasting time of your life here talking to myself about it. I would think that if you got that much time to waste in your life, then you should waste it doing something that you have an interest in. All right. Now that's a noisy signal. And let's see, coupling, ground, DC, channel 1, coupling, DC, and we're going to turn them both volts there. All right, there we go. 1 volt, 1 volt. Okay, so I've got my scope here set so that my shit can fall on the floor and not do anything. Put this up here so it'll stay, and you can really just see how it's setting up. Actually, it looks like there's a little bit more than a 50-50 divide here. I'm seeing should be showing 1 volt. Why isn't it showing 1 volt? Alright. Weird. Milo, calm down. Well, I have to get my probe back to where it's supposed to be. So I'm gonna mess up my shit. Okay. So my channel 1 is giving me weird readings on the measuring peak to peak, and that's because it's looking at peak to peak, and this is DC. Doesn't really give me a DC. I don't think. Let me see here. Measure voltage, channel 1, peak to peak. Add 9.2. It's 0.92 volts, 920 millivolts. And let me see, channel 2. Add that on there as well. So yeah, you can see there's a pretty big drop across the inductor there. So giving me quite a bit more drop than I'm expecting. According to this, I got 920 average on my out of here, and then I'm reading 280 millivolts on my output. So that's a difference of .6465. 280, 920 minus 280, so 64 millivolts. 64, yeah. 640, yeah, so 0.64 volts. There. All right. Now let's take a look at the AC, right? Before I do that, I'm gonna obviously show you the output of the scope, what it looks like now, so you can see, and then we'll turn on the function generator, so you can see the way the voltage drops are happening and what this frequency has to do with it. This is some really cool shit that a lot of people just don't know. And it has a lot to do with your electronics, and not just amplifiers, but everything. So I hope that the people out there that are trying to be insulting and they see this, they learn a little something, and they value that knowledge that they gain, because, you know, this is stuff that people use when they're talking about electronics, and most of the people that work in electronics that have done it for a while, or maybe just starting out, they all know this shit. They learn it, and they fucking, like, look at me, dude. I have no notes around here whatsoever. I'm just literally surrounded by a bunch of components and breadboards, and I've got packages of different components. Some of them are open right now, so I can't pick them up. But at the other time, you know, like these, you know, and these, you know, I've got a whole bunch of this stuff just kind of laying around, and I tinker with it, and a lot of times I'll find solutions to things about work while I'm playing around with this stuff in here. So knowing this stuff is very important if you want to do electronics. So let's check this stuff out. I'm going to show you the DC waveforms real quick, and then we're going to check out the AC waveforms. All right. Okay, so this is the output of the inductor with a DC waveform. This is a 1 volt. This here, it's approximately about 400 millivolts, about half a volt, give or take. So says our average is about 980 millivolts, which is approximately 1 volt. And our average output is 400 millivolts, which is approximately half a volt, which means that these two things have approximately the same DC resistance, getting about half the output, 100 ohms. Okay, so this is the output of the inductor with a DC waveform. This is a 1 volt. This here, it's approximately about 400 millivolts, about half a volt, give or take. So says our average is about 980 millivolts, which is approximately 1 volt. And our average output is 400 millivolts, which is approximately half a volt, which means that these two things have approximately the same DC resistance, getting about half the output, 100 ohms. Okay, folks, so this is our output at a really high frequency of 10 kilohertz. The yellow line is our input. As you can see, it's got a pretty nice, good size swing on it, but our inductor here has barely got anything going through it. As a matter of fact, our signals are scaled down. So this is 200 millivolts per division for our input. Division is the distance between this line and this line here. And our output here is at our lowest possible setting, 20 millivolts per division. So again, same unit for division, but it's only 1/10 as much. And of course, this is because of the reactance. Now, I mentioned a frequency earlier that we were able to find by doing a little bit of math. Oh, you can see those spikes on there. Those are caused from changes in the voltage going through there. So voltage changes, it causes an inductor to release a bit of current. So that's why you get those spikes with the noise spikes in the signal. But we're at 10K. Let's go ahead and change our frequency here. There we go. Now we can move up a few more divisions. So here we see our signal. We're still at 200 millivolts per division for our input signal. Dropped it down to 1K, and our output signal, we're still having it at about 50 millivolts per division. So that's at 25%. So this one is technically more than 4 times this one at this lower frequency. Now I'm going to start going down by a little bit lower frequency here at a time, going down by 100 hertz per click. 600 hertz. Tighten this up a little bit. As you can see, we're starting to grow on it. We're still 4 times at the magnitude though. So we'll turn this back up. So now we're getting at about 50% there. So we're at 100 millivolts per division for our output signal. Still 200 millivolts per division for our input signal. Input signal is much larger than it seems to be doing, but let's go and check it. We should be getting 100 hertz. Oh. Now we're at 100 hertz. We're getting, well, we're in the same scale, right? Almost half the signal, and we're really close to the frequency that we were looking for. Little interruption there from me tapping things here. About 50% is what we're looking for when the impedance of the inductor is the same as the impedance of the resistor. We should see these at approximately 50%, right? So got me an unreliable connection with my scope probe. And some noise. So let's try this by moving to let's see, frequency 160. I believe I said 141. And getting really close there. The thing is that we're never going to get it exactly on there, right? Mostly because we don't have the best probing going on here, and there's a lot of noise going on in the room. But you can see how the frequency is affecting it. The lower I go in frequency, the less impedance it's offering. Now, let me see here. I'm going down 1 hertz at a time. We want to go down a little bit faster than that. There we go. We almost got them overlapping each other right there. (13 hertz). very low frequency. And here they are at the same time, at the same scale. You can see there's still a bit of a voltage drop there, right? Well, that's the resistance. The impedance, or the reactance, I should say, is virtually non-existent. But that's what it is, man. That's all it is. Okay, so you may have noticed that there was a little something going on besides just the drop in voltage. Now, of course, you expected about half of the input voltage to be there at the output because of the resistance. But you probably noticed that not only was the voltage less at the higher frequencies, but it was kind of moved to the side. And it was the opposite side of what the capacitor was doing. It was like everything. Well, that's because this is reactance, which means that your additional voltage drop besides the resistance of the inductor is actually the result of the phase shift that's caused by the inductor's inductance reacting to the changes of the current. Now, this is a sine wave. There's changes happening all the time, and a lot of these spikes that you're seeing, especially at the really high frequencies, you're seeing a lot of spikes coming through on the output. You still see those spikes now, even with no signal going through, just because it's got a little bit of voltage in the air, you know. And these things with the signal coming through it, the inductor is tuned really well for high frequencies. So radio waves in the air are picked up by these things really well. They actually work like an antenna. That's why inductors are used in antenna designs. Inductors and capacitors are used in antenna designs. And if you're somebody who's learning electronics just because of your interest in amplifiers, particularly old amplifiers like vintage tubes and shit, then something like an inductor may not be all that exciting for you, right? But if you want to learn electronics for the sake of knowing electronics and all the different aspects of what electronics is, well, the inductor is super fucking exciting. It's one of the coolest of the it is the coolest of the passive components, because just like the capacitor, it has a lot to do with resonant frequencies. In our next video, in fact, we're going to talk a lot about resonant frequencies and how inductors and capacitors play together to give us a resonant frequency, which I've seen videos from even what's his name? Will's Easy Guitar, Will Gelvin. I've seen his video where he talks about this resonant frequency stuff, and he's somebody that a lot of people think, you know, he can't be wrong about things, but even he is capable of mistakes, and he makes one that I could think of, but I'm not going to spend a lot of time calling him out. But if you're watching my last video, I made a mistake in that video. And I made it on purpose. And if somebody guesses it, I don't know. I'm thinking of something that I could do, and I'm willing to take suggestions from the folks out there at YouTube that give a fuck. But in the meantime, thanks for watching. Have a great fucking day.